Welcome again. Today we look at the topic of acids and bases, taking a look first at the work of Arrhenius in an original definition of acids and bases, and then considering how that definition gave way to the Bronsted-Lowry theory of acids and bases, as we look specifically at what constitutes the Bronsted-Lowry definition of an acid and a base. And we will define examples of Bronsted-Lowry acids and bases. And then, building out of this definition of acids and bases given by Bronsted-Lowry, we will identify conjugate acid-base pairs and consider ways of identifying the members of a conjugate acid-base pair. So let's move in and take a closer look.
According to the Arrhenius theory of acids and bases, acids ionize in water to produce H+ ions or protons, and alkalis are soluble bases which ionize in water to produce hydroxide ions. A reaction between an acid and an alkali is a neutralization. A typical example then is hydrochloric acid and aluminum hydroxide to produce aluminum chloride and water. But what about a case like this? Ammonia, which today is defined as a weak base, reacting with hydrochloric acid to form ammonium chloride. If it is that ammonia has to be described as a base, then the Arrhenius definition of acids and bases was clearly not sufficient. So the result was a paradigm shift in what was considered to be an acid or a base. And the Bronsted-Lowry theory of acids and bases considered an acid as a proton donor, very much in keeping with Arrhenius. But as far as a base goes, a base was defined as a proton acceptor. And with this definition from Bronsted and Lowry, it was possible to include this example and to justify the proton accepting behavior of ammonia as being typical of a base, a proton acceptor. And here the proton donating nature of hydrochloric acid fits the definition of a Bronsted-Lowry acid, a proton donor. With this definition from Bronsted and Lowry, it was then possible to identify examples of conjugate acid-base pairs. Here you can see sulfurous acid plus water to produce HSO3 negative and H3O positive. Here, HSO3 is behaving as an acid as it donates a proton to H2O, which accepts that proton and in so doing behaves as a base. H2SO3 then becomes HSO3 negative. The conjugate acid-base pair being these two, with here a proton being donated to produce this, and if the reverse reaction were to happen, then HSO3 negative would accept a proton and return to the acid. So you would realize that the difference between the two members of the conjugate acid-base pair is the presence of a single hydrogen ion or a proton. A donated proton from HSO3 gives rise to HSO3 negative. And where you have one conjugate acid-base pair, you're going to have another. Because as this acid donates a proton, a base would have to accept it. And here, H2O behaves as a base, accepting a proton, a base, a proton acceptor, to form H3O positive, the hydronium ion, which is the conjugate acid of H2O. And when the hydronium ion gives off a proton, donates a proton, it behaves as an acid and it returns to H2O, which is the conjugate base. So again, the difference between the members of a conjugate acid-base pair is the presence of a single hydrogen ion or a proton. Now it's your turn to identify some examples of conjugate acid-base pairs.